Hi everyone, welcome back. So before we go any further, before we can get to conservation momentum, we need to talk about something called the material derivative. And it has various names, so if you see this and you're like, wait a second, that's actually this. That's fine. You can call it what you want. For this video, material derivative. Now what is it? It's this. So when it's written out, you always have a capital D derivative with respect to time. But it's not just with respect to time, it actually has a lot more to it than that. It's a shorthand way of showing this. Now, this by itself probably doesn't look that important to you, but let's go ahead and put the mass flow rate in there, the density times the velocity in there. And when I put that in, what I see is the following. So I have my density times velocity, and it's shot into all of these. Like, okay, well, why is this still important? Well, each of these terms actually means something. So let's focus on that first time derivative term. So this one actually stands for traditional acceleration, simply meaning that if I have a particle and I'm just looking at it with respect to time, its velocity may increase or decrease. So that term is always talking about this traditional acceleration. The second terms here, they're actually talking about convective acceleration. So they're saying, okay, if I contract, if I expand, that's going to change the velocity of my particle. If my particle is closer to the walls or further from the walls, it's going to change the velocity of my particle. And so this convective acceleration, where I have my geometry causing the change in my velocity, rather than maybe a force or something, is what the second term is doing. So it's giving us both types of acceleration for our fluid elements. So that's the reason we have that there. And that's why it's very, very important. So when you see this capital D, capital T, know that it's always talking about this. And we won't see it very often because we'll often make a steady state assumption. And if we do, well, this whole thing goes to zero as well. It disappears. At least most of it does. I say most of it. That was terrible. That part goes to zero. A small portion of it goes to zero. Okay, there we go. But thanks for listening, and next time we'll jump into conservation momentum. And it's a doozy, but we're going to simplify it, so do not freak out. Have a good one. Bye-bye.